Yeah, so we're very happy to have Cheuk Yu Mak, and I'm really sorry if I didn't say it right, from University of Edinburgh, talking about non-displaceable Lagrangian links in four manifolds.
Yes, thank you, Shara. Thank you for the introduction and invitation, as always. And I'm going to talk about some disconnected Lagrangian submanifolds and its non-displaceability. And so before that, let me start with a famous saying from Elias in regarding symplectic topology. Sorry. Yes, so he says that in symplectic topology, so if something is not obstructed by J holomorphic curves, then it should be flexible. So yeah, this is one of the first philosophy I've heard when I started my graduate school, and then
let me make a comment. I think there's a less famous thing saying this is wrong, but anyway.
Oh, okay.
I think it's almost. I mean, it's close to be correct, but I think there is something else.
Yeah, that's a very nice comment. Yeah, thank you for the remark.
Helmut's very protective of his J holomorphic curves.
So right. So first of all, this sentence doesn't have a very precise and rigorous meaning. So we kind of try to understand this by example, or try to say that it is wrong by giving counterexample. But let me first give an example to support this philosophy. So, and so this is the simplest example for people who learn Lagrangian floor theory. If we have a sphere together with a circle lying inside the sphere, separating the sphere into two regions of area A and B, then we know that L is non-displaceable if and only if A equals B. So there are several ways to prove this. So one option is that, of course, because Hamiltonian diffeomorphism preserve area, so you can use area reasoning to show that it is true. So if you prove, I mean, at least you can prove one direction using area reasoning. And and another thing is that you can prove it using Lagrangian flow cohomology. If A not equal to B, if A equals B. So this is something that involves J holomorphic curves, and it is indeed shows that the philosophy is true for this example. So but it is very natural to ask, what if we consider, again, the symplectic manifold is a sphere, but we consider a Lagrangian to be a disconnected submanifold inside, which is the union of two circles, separating the sphere into three regions of area B, C, and B. And L is the union of them. So in this case, it is by the same by area reasoning. You can convince yourself that when C is small, so when L1 and L2 is sufficiently close to the equator, then the union is actually non-displaceable. So when C is less than or equal to 2B, L is non-displaceable. And even more, if C is less than or B, any connected component is non-displaceable from the union. Non-displaceable from L. So the question I want to ask in this talk is whether we can prove it using J-homomorphic curve. I don't want the page bar.
Okay. Yeah. How did it go? I think no one understood anything. Oh no, why? Huh? Why? Just because I was a bit ambitious.
So, right. And question is whether we can prove this result using J-homomorphic curves. And even what is even more interesting is that what if we consider, so what if we stabilize our manifold by these by we take the product Li equals to Li cross K, and K is the equator. And the question is L, which is the union of these two, non-displaceable when C is small, when say C is less than B. And surprisingly, the answer is it is actually displaceable as long as the factor on the right-hand side is large. Oops, displaceable when 2A is greater than 2B plus C. If the factor on the right-hand side is greater, has larger area. And the result I want to talk about today is it says that it is actually non-displaceable when A is small. L1 is non-displaceable from L when A plus C less than B. And okay, so what is the idea? The key idea here is the following: is to somehow make use of the J-homomorphic annulus bounded between the Lagrangians L1 and L2. So we are not the first people to use holomorphic analyze, and holomorphic analyze have been used by many people before, and for example, one situation that it appears is when you pass to symmetric products, and consider especially when you consider the Higa flow theory. So let me recall a little bit. So holomorphic analyze appear in Higa flow as follows. So if you consider, if you have a manifold, and if you consider your L is a collection of pairwise disjoint Lagrangians inside, and you have two such collections. Let me call P K1 up to Kp. Each collection is a collection of pairwise disjoint Lagrangian submanifolds, and what you do is you consider the product. Sorry, you consider the product inside M to the P, and then descend it to the quotient. Descend it to the symmetric quotient, M to the P, modulo the symmetry group. And then we denote this quotient, the image to be sim L. This is the notation. And what you do is if you consider the Lagrangian flow cohomology between these two Lagrangians, then this guy can capture holomorphic curves bounded between them. More. Bounded between them. Between the union of Li and union of Ki. So the check that we are going to use is simply passing to symmetric products. And okay, but let me explain then I need to explain two things. One thing is how is it related to our original problem? Our problem that we started with about the non-displaceability of the union. And the second question is how these holomorphic curves enter the story. How do these enter the story? So which means that I have to explain why symmetric products can capture small holomorphic curves. Okay. Any questions so far? Okay. So the answer to the first question is, so if you think about it, if this guy is displaceable from the union, then say by a Hamiltonian phi, then the symmetric product of this one and the sim of this one will be empty. So if you can displace one of the connected component from the union downstairs, then you can displace it upstairs after passing to a symmetric product. So it means that if this guy is non-displaceable, then so is L. So our focus is therefore becomes the non-displaceability of this Lagrangian. This will be our focus. And now I want to explain how these holomorphic curves, how are the holomorphic curves in symmetric products and holomorphic curve in the original manifolds are related. So they are related by something called tautological correspondence. So it says that it appears in a lot of work. For example, it appears in the work of Donaldson, Higafro, Oswald Zabel, and Costello, and so on. It appears in a lot of people's work. And it goes as follows. If you have a Riemann surface, and together with a branch covering to a disk, say K to 1 branch covering. And if you have a holomorphic map from the sigma, from sigma to M with boundary on the collection of Lagrangian L. Is someone typing? So yeah, thank you. And so the data of pi sigma and V together is equivalent to the data of a holomorphic map U from a disk to the symmetric product. Okay. Maybe this is P. So this guy is a union of P connected components. I from 1 to P, Li. So sim M, sim L. So the relation, so the data of U and the pairs of map V and pi sigma tautologically related in the sense that one determines the other. And in one direction, if you have V and pi sigma, so you can define U to be, you first take the preimage of a point, so Z is a point in the disk. You take the preimage to get P points in sigma counted with multiplicity. And then you push it to M. So sorry, this is P. Right, so this is how the correspondence goes. So for example, if you consider an annulus with a 2-to-1 branch covering to a disk with 2 branch points, and if you consider a map, a holomorphic map V from an annulus to say a sphere like this, you map to the cylinder in between. And these two maps together will determine a map from a disk to the symmetric product of the disk. Yeah. So the example. So And morally, because it captures, passing to symmetric products captures more holomorphic curves. So morally, we should expect that we can recover more information of the original manifold M from passing to symmetric products. And in the rest of the talk, I want to explain in more details how to incorporate this idea and to prove the result. Prove the theorem using this idea. And and the main machinery that I'm going to use is the superpotential theory developed by Foucault, FOO, and Cho Porter. Any questions so far? Okay. So let's quickly recap the theory of superpotential. So let M be a compact symplectic manifold or orbifold. And L is a torus, is a Lagrangian torus inside such that it bounds no Maslov less than or equal to 0 disk. And, and such that it is away from the orbifold locus. Then and we also fix a basis for the first homology of L. And in this case, the superpotential will be defined as sum of counts of Maslov 2 disk in the class A, and together with times t to the corresponding power of the exponent being the area of the disk, and x to the boundary A. So this is the side count of Maslov 2 disk with boundary on L and class A. And and boundary A is the homology class of the boundary of the disk. X to the power A is pi xi ai. So in this case, what they prove is, in this setting, what they prove is if W admits a critical point X lying inside the Novikov ring deleted by the maximal ideal to the power n, then the flow cohomology, the deformed flow cohomology by X will be the same as the cohomology of L itself, the exterior algebra. No, it's, I mean, it's a vector space. And L is non-displaceable. And there is a generalization of this story by including bulk deformation. So if you pick a cycle, say codimension 2 cycle inside your manifold, and also an element inside the maximal ideal of the Novikov ring, then you can define a bulk deformed sphere potential. And it will involve counting the contribution of a holomorphic disk will be modified by this bulk. And so I assume Q is a codimension 2 cycle, and it will look something like the following. Look something like this. MAKQ B to the K over K factorial T omega A X boundary A. So this guy is counting disk which pass through the cycle K Q K at K interior mark points. And this is one generalization, and there is also another generalization to the orbifold setting by Troy and Porter. So and when M is an orbifold, so you can pick Q to lie inside the orbifold twisted sector. So say for example, if our manifold is a global quotient of if our orbifold is a global quotient of a manifold by a finite group G, then we define for each conjugacy class we define this to be the fixed point for G lying inside G. So for each G lying inside G, each element in G, and it determines a conjugacy class. And for each conjugacy class, we have a corresponding so-called twisted sector, which is defined as a fixed point set of X quotient by the centralizer of G. So so for example, M of E will be M itself. E is the identity element, and and in general, we have other orbifold sector, and the inertia orbifold is the direct sum over all the conjugacy classes over these twisted sectors. So if you pick two different elements in the same conjugacy classes, they will define the same twisted sector up to isomorphism. So I only take the product over all conjugacy classes. A disjoint union over all conjugacy classes. And and why am I talking about this twisted sector? The reason is that we can do bulk deformation using bulk inside. And why can we using bulk deformation using bulk inside? The reason is that the evaluation map naturally lands in the codomain of the evaluation map is the inertia orbifold instead of just the orbifold itself. So because as I drew in earlier picture, when we have a branch covering, then our disk will have some orbifold point, some branch point, and the map U is actually not a holomorphic. So the domain of U is actually an orbit disk. So this is a U is a whole map of a holomorphic orbit disk, and so the evaluation of this interior point, if it is an orbifold point, then the evaluation at this point will naturally lies in certain orbifold sector, some twistor sector, not necessarily this one. It will lie inside the image of evaluation map will lie inside here. MG. Too many P. Let me call it Z. Z. Evaluation map. So, and because this is the nature of the evaluation map of interior mark points, so that's why bulk inside other twistor sector of inertial orbifold will appear. And in our case, we need to so there is a corresponding theorem of sphere potential and critical points in this setting.
Inertia orbifold different from just the quotient of m by g. The inertia orbifold in the previous page. So that's like this disjoint union, but isn't that just equal to x mod g, or maybe I'm just
so only the first one, only this one, only if you take the conjugacy class of the identity element, then you will get this. But if you take something else, g not equal to e, then it is not m.
I see.
So this is a disjoint union of a lot of orbifolds.
I see. So this is not like the orbit type stratification on the original orbifold, but it's more
no. Right, this is something else. But it is extracted from the orbifold stratification you mentioned. And so let's see an example, very simple example. So now back to this guy, BCB, a sphere with two circles inside. So in this case, I want to use twofold symmetric product. So is m cross m divided by C2. So our G only has two elements, and ME is M, and M not equal to E is essentially the diagonal. So diagonal inside M cross M. No, that's a very I mean, seem to no. Once again, sorry. Yeah, X, ME, X. Okay. X. Okay. So anyway, and so now if we want to compute the sphere potential of this guy, L1 union L2, then so you want to look at the sphere potential, and if you if you don't turn on bulk deformation, then the only contributions will be the disk here, x1 t to the b, and the other disk here, x2 t to the b. So this is something we don't want because it doesn't have critical points. But if we turn on the bulk inside, if we use this to be our bulk, then what it is saying is that we are counting contribution we start to count orbit disk because the orbifold points in the disk will be the interior mark points of the disk, and their evaluation when the orbifold points is not a smooth point, the evaluation will go to this twisted setter, and so we will have something like x1 inverse, x2 inverse, t to the power c, corresponding to the annulus here. So what I'm saying is that there is an annulus mapping to this guy, c here, mapping to there, and together with the 2 to 1 branch covering to a disk with 2 orbifold points, then the corresponding map U in the symmetric products will be a holomorphic orbit disk, and the total contribution will look like this. And the 2 here comes from the 2 orbifold points in the domain. So basically, turning on a bulk in the orbifold setter can capture some orbifold disk, and in this way. And you can see that, and there might be some higher order terms. And you can see that, at least if you look at the first 3 terms, you can see that if C is less than B, then you can find B such that this guy has critical point. Has critical point in the complement of the maximal ideal inside the Novikov ring. So this is a 4th theoretical way to prove that the union is non-displaceable. So of course you can use area reasoning. So this is a very fancy way to prove this non-displaceability. But now we can back to the question that we are more interested in, which is this guy, ECB cross A. And so the key point here is that the same idea works, but here we have something a little bit tricky happens, which is if you remember the results of proto-origin, when A is large, the union is displaceable. So so it means that the area of the second factor somehow will affect the 4th theory of the symmetric product. And the reason is as follows. The reason is that it turns out that the superpotential, it turns out that the annulus that we want, the annuli that we want, so it's a map V from V1, V2 from an annulus to this guy, M. And the V1 is a degree 1 map surject onto the middle region, as you can expect. But the second map is a degree 1 map surject onto a hemisphere. This is the thing that we want. So that's why the A will be relevant. This number A will be relevant to the computation of the superpotential, and this is the main reason why yeah it is relevant. So but why is it the annuli we want? The reason is that these are the annuli with the correct virtual dimension, and you can ask, how about the annuli that's only subject to this factor, but is a constant map to the second factor? So how are they playing any roles? So the role they play is those naive annulus, those annulus, those annuli actually leads to Maslov zero disk in the symmetric product. With boundary on this Lagrangian. So this is a situation that we don't want. So and ultimately, what we need to do is we need to apply the Fukaya trick to move this guy away from this wall, from walls, in the sense that this guy will no longer bound holomorphics, no longer bound Maslov zero disk. So I'm quoting this Maslov zero because this is an orbit disk. So this is not the Maslov zero in the original sense. So but the phenomenon looks the same. So we need to move it away from the wall so that it no longer bounds Maslov zero disk. And then we can show that it doesn't bound any. So that's why it also doesn't bound any negative Maslov disk. And so the theory applies, and one can show that the corresponding superpotential has a critical point. And but instead of giving the calculation, I would like to use a picture to illustrate what is happening in a more intuitive term. So the picture I want to use is the moment image of this S2 times S2. So we have a factor of S2 which has smaller area, S2A, S2A with area 2A, and another factor here, a sphere with area 2B plus C, which is larger. And then our Lagrangian, our disconnected Lagrangian is union of two moment map fibers. So L1 and L2. And the annulus that we want looks like this. If you perturb it a little bit, they will merge to become an annulus. And the annulus that we don't want looks like this. So after applying Fukaya trick, what it looks like is the following. We perturb it a little bit, such that the slope between the 2 points is an irrational slope, is an irrational number. And then in this case, there will be no Maslov zero disk there will be no Maslov zero annulus with boundary on these two Lagrangians, no non-constant one. And then the interesting one is still here. So after applying Fukaya trick, the green one disappears, but the orange one stays here. And so so of course the projection of the annulus will not look exactly like this. But what I'm using here is a tropical interpretation of what one would expect the holomorphic curve would look like. And you can see from this picture all the essential contribution of the superpotential, which so we have this annulus, and then we have another annulus looks like this, and then we also have some other terms, which looks like the disk here, disk here, the disk here, the disk here, the disk here, the disk here, and the disk here. So these are the most basic terms in the superpotential, in the bulk deformed superpotential. And I find it so right. Any questions so far? So okay, and
so maybe can you explain a bit more how you move away from the walls and drop the Maslow's zero disks?
Yes, sure. Thank you for the question. So the way is so we consider the diffeomorphism. I consider the diffeomorphism of this guy, of our manifold, such that C2 small, sufficiently small, such that the image and of Li, L1, and the image of L2 are torus fibers, Lagrangian torus fibers, with irrational slope, in the sense that the line connecting these 2 points has irrational slope, and some basic complex analysis will tell you that because you can project it to the 2 factors, so will tell you that these 2 guys, there does not exist any holomorphic Maslow's zero holomorphic annulus. With non-constant, with boundary on these 2 guys, phi L1 and phi L2, and then now standard J holomorphic curve with boundary on this guy is the same thing as either push forward or pull back. I don't know. With boundary on L1 and L2, push forward J. Am I correct? So L1, L2, J, phi J, pull back. Okay, yeah, and J holomorphic curves. So as long as this guy is a omega team, then you can even make it compatible. Then using the counting of J holomorphic curves here, you know that there is no Maslow's zero holomorphic annuli with boundary on these 2. So that's how you move away from the wall, and then you can and you can also construct this guy, this annuli, directly. So here I only draw some tropical picture, but actually you can write down the map explicitly for with boundary on these 2 Lagrangians, and then so yeah, I find this tropical viewpoint and it's very helpful to me to understand what is happening and all the holomorphic curves there. And but I want to finally make a remark that this tropical holomorphic correspondence is actually not correct when the number of boundary component is more than 3. And so this picture is really just I mean, as a guide, but not really something that you can rely on very seriously. And this tropical holomorphic correspondence can break down if you have more complicated situations. Okay, maybe that's the end of my talk. Thank you.
Thank you very much. Any questions?
Maybe I have a little question. So, do I understand correctly that even if you wish to work just with S2, you need this stabilizing factor in order to get rid of orbital disks of index 0?
Yes.
So somehow you cannot just work with symmetric product of S2 with itself. Yeah.
We are working with symmetric products of. We are moving this guy away. We are only moving the Lagrangian, but not the ambient manifold.
My question was the following. So assume that you want to reprove the trivial fact that these two circles are non-displaceable on S2, but
yes.
with the help of holomorphic curves.
Yes.
Okay. So then you have to stabilize first. So you have to multiply regional S2 to the smallest 2 and then do what you are doing, because
yes.
the annulus which you see on the sphere without stabilization is kind of useless. It has a wrong Maslov index.
Right.
So this is this correct understanding that even in a sense, even for the two-dimensional result, you
for the two, oh, you mean for the two-dimensional result, this
yes,
one?
Yes.
Oh, I see. For this one, we don't need to. This is actually not useless. This is actually useful. This guy actually has the correct Maslov index. It will lift to Maslov 2 disk. This cylinder. So this is the difference between ambient manifold being dimension 2 or dimension 4. In the case of ambient manifold is dimension 2, then the Maslov 0 annulus, Maslov 0, will go to Maslov 2 disk. But if the ambient manifold is a dimension 4, then Maslov 0 annulus will lift to Maslov 0 disk. This is some feature. So this is some feature that I think is very good that you pointed out. Yeah, and it has to do with the fact that only in complex dimension 2, the symmetric products can be resolved by the Hilbert schemes by a Krepler resolution. Only in complex dimension 2, this is correct. It has to, so it means that the canonical bundle can be pulled back to a smooth one. Because in complex dimension 2, that resolution is a Krepler resolution. And in higher dimension, so for example, in higher dimension, the Maslov 0 annulus will go to Maslov -2 disk if your ambient manifold is dimension 6.
Mm-hmm.
Yeah.
Thank you very much.
Yeah, how much of the story might work in higher dimensions?
Yeah, that's a good question. So actually, in higher dimension, the main problem is the following. In higher dimension, is again the problem of this Maslow's zero thing. So what could happen is the following. You could have some high genus thing, say Maslow 4. But if you leave it to a disk with if you leave it to an orbifold disk, then it will become Maslov 0. So it means that in a priori, this kinds of thing in M can obstruct the Lagrangian flow theory in the symmetric product. So to have a unobstructed or weakly unobstructed Lagrangian in Sim K, and if the ambient dimension is greater than 4, then you need to rule out all these kind of things, some higher genus, high Maslov index things. So this is some difficulties that I encounter, and so that's why I spend a lot of time studying these how these holomorphic curves map, how these tropical holomorphic correspondence, and how holomorphic map to this kind of algebraic torus of higher dimension, or some P1 to some power. And this is some nice complex analysis thing to look into, and and I realized that yes, to generalize our results to higher dimension, this is one thing that we need to overcome.
Thank you.
Actually, I have just a follow-up question, right? So you explain, I mean, this is the difficulty that you face, but are you optimistic, or are you hopeful that such results could be proven for, say, CP2? And the Lagrangian tori instead of circles?
So in CP2 for this one, right? Mm-hmm. So for CP2, actually one can easily check that the pseudo potential will not have critical points if you take some disjoint union of torus fibers that doesn't contain the monotone one. I mean, so for the answer for CP2 is that I don't think our method directly applies for CP2, but it will apply as long as your moment polytope has parallel edge. It will apply as long as it has parallel edges. So it covers infinitely many examples. So you can put anything here, no matter you want, as long as it has parallel edges. Then you can show that. So the Lagrangian tori here, you can find some disconnected pairwise disconnected pairwise disjoint, not pairwise disjoint Lagrangian tori there, such that the result is whole, is true.
Oh, so the result is what?
The result is you can find so it looks like this. The result is you can find this L1 LK, or maybe you can just do 2 points, and then L1. So this is a four-manifold now. M is four-manifold, and this is the moment polytope of M with parallel edges, and L1 is non-displaceable from the union of Li. Non-displaceable from the union of Li. You can find, and you can find such things, and yeah. Sorry, as long as the parallel and parallel edge together with the distance here is small. It cannot be too large. A small distance here.
So if you fix L1 to be some small Lagrangian torus, then can you determine like a large enough K such that so you have some sort of a maximal Lagrangian packing?
What do you mean by maximal Lagrangian packing?
I mean, if you have, there's some K such that if you go to K plus 1, then you can't have some K plus 1 disjoint copies of this small Lagrangian torus. I mean, I guess, wait.
What do you mean? So you can, the K here can be arbitrarily large.
Okay.
But they will become, yeah, actually you can read, there is a paper on arXiv today. So
yeah. No. I just,
you can read.
All right.
by I should say, by Potorovich and Shalukin.
Right.
So, and they have a nice application to Hopper geometry of sphere.
No, yeah, I saw that actually. I just realized I'd seen that this morning or very recently. Okay. Thanks.
Yeah, thank you for the question.
More questions?
I have maybe not a question, but a little comment related to your initial, to Yasha's philosophy about rigidity and and curves and J-holomorphic curves. So my comment is that this is obviously a vague statement, but one can make it more precise today in some ways, in the sense that there are a variety of metrics that you can put on Lagrange, on spaces of Lagrangian submanifolds in particular. And in fact, generally the construction gives you pseudometrics. And then the question is when these pseudometrics are in fact non-degenerate. And so you can analyze this question whether you have or not rigidity, and whether rigidity is equivalent to unobstructedness of the class of Lagrangian submanifolds. So of course it's not known, and as Helmut was saying, maybe it's not true in this generality, but there are cases where it is true, in the sense that you can show that these metrics are non-degenerate precisely when the manifolds are unobstructed. And in any case, you can formulate this explicitly, as a problem that to be, not just as a general philosophical question, but just looking at these metrics and deciding whether they are pseudometrics, deciding whether they are or not non-degenerate.
Right. I think everyone has his or her own take of what rigidity question he want to ask. So one could ask not necessarily Lagrangian, or ask about some Hamiltonian, or I don't know, few things.
The difficulty there, it's a little bit, I mean, the difficulty to define these things is that you want them to be some measurements that are finite on a large class of objects. And then when they are finite, the question of whether they are degenerate or non-degenerate is very, becomes delicate.
I see.
And of course, objects can be Lagrangian submanifolds. Maybe there are other objects that one can consider. But I'm just saying that there is a way to look at this problem in a rigorous way. And
could you give an example? Sorry, I'm asking you question back.
I have a paper about it. I have a paper with Paul about it.
Okay.
It's called the Lagrangian Pictionary.
Oh, okay. Yeah, I'm aware of that. Yes.
Yeah, look into it. It's we kind of found that this is actually it's also a bit related to this C0 type topology, because these metrics fit with C0 topology, in fact. But in any case, it was just a comment. I mean, you can take a look there. I don't want to take from your time actually talking about this, but I just...
Yeah, thank you. Thank you for the comment.
Yeah, so coming back to my earlier comment. So, I mean, in dimension 4, I believe that more or less pseudo-holomorphic curves capture what, the obstructions. But in higher dimensions, I'm not so sure. I mean, I think it's presumably a rather fragile thing where at the bottom of it are holomorphic curves, but I think there might be other things before which, however, are not that rigid and can collapse into smaller things. So, I mean, so Yasha and I, after Yasha already had done his theory, so we had this result where you have a pipe and you have a contact flow. It's standard on the boundary. It's in dimension 4. Yeah, it's a 3-dimensional pipe. And then if not all the trajectories go through, then there had to be periodic orbits which capture, in some sense, the obstruction inside Reb orbits. Yeah? So if there were no Reb orbits inside, everything goes through. Periodic Reb orbits inside, everything goes through. Of course, a priori you could think there are other things which obstruct this. Yeah, but the obstruction in that case, in dimension for this 3-dimensional thing, was captured by a periodic orbit inside. And then we had the conjecture that this is true in higher dimensions, that if not everything goes through, it's captured by some configuration of periodic orbits. And that was shot down. So there are examples where nothing goes through, there's something complicated inside, but this is not expressed in terms of periodic orbits and so on. It's not so clear. If perhaps one can put some structure based on some perturbation which has periodic orbits, I don't know. So this was a paper by Geiges and Nena, I don't remember the name. So there were several people, Zemisch, and Nena Röttgen. And that was sort of surprising because we thought at the beginning, periodic orbits and chain complexes built on this should be some obstruction for this. And that turned out there's no periodic orbit, but but there is some obstruction, which can be a really messy set. So I don't know how one can capture this by some more elaborate holomorphic curve construction. So that's one of the reasons.
So for this matrix I was talking about, the only thing we know is that there are some cases when there are not non-degenerate, and in all cases where the H principle applies, they are completely degenerate. Mm-hmm. And so, okay, there's a lot of room in the middle. And but one can, so the idea behind this matrix is that in symplectic topology we have a big mixture between algebra, like triangulated categories, and this construction based on taking cones and measurements, and you can mix them up and they lead immediately to metrics or pseudometrics. Mm-hmm. And this pseudometrics capture spectral invariance and things like this, and also all sorts of measurement, energy measurements. And then it's natural that they are sometimes non-degenerate when all the theory is unobstructed. One expects that. And also one expects when everything is flexible, they should be completely degenerate, because I mean, and then, okay, so, but you can formulate the question at least in a more, slightly more rigorous way.
Mm-hmm. Do you have a candidate example that is sitting in between?
I don't, but that's why I mentioned the question, because I found the start of your talk very, very stimulating to think about this stuff. And it's a question I thought about a long time ago, about the boundary between rigidity and flexibility. So this boundary seemed to be like a line at some moment, but now to me, it seems like there is room there for some things. And what Helmut says, it's like something that will be somewhere there in the middle.
Yeah. So, for example, if you look at so embedding problems, and for example, you in higher dimensions, simple things in R2N, and if they are rather roundish, you see more rigidity than if they are very longish. And the question is that just captured by pseudo-holomorphic curves or nothing? Roundish looks to me like a phenomenon which also is seeable in higher dimension. Should have a higher dimensional aspect to it. And there's a paper by Ambodandolo about, and I don't remember who else, some time ago about embeddings, but where you assume the image is convex of the embedding. Then you actually see higher dimensional stuff.
Mm-hmm.
Yeah, but you can't capture it really very well. So the picture could be, there is, if things is, say, close to linear, let's say, then you have higher dimensional stuff. And then if you make it really wild, this higher dimensional stuff just deteriorates to low dimensional stuff. Yeah. So something of that kind.
Mm-hmm. How did he capture that?
Well, you have to look at this.
Okay,
He works hard and makes estimates using the convexity of the image.
Okay.
Yeah, so that's an interesting point. And we know convexity is an important quantity, even if it's not symplectic, but it captures something which we haven't understood yet. Yeah, just saying convex. So there should be something symplectic. And I think convexity has ramifications I mean, there's something to be measured in all dimensions if you have a higher dimensional object, the symplectic stuff. And then when you turn it into something which is not convex and so on, then things start collapsing. And at the bottom is Yasha. So I think that's a better picture. So Yasha's statement is the Fourier coefficient of a whole thing. It's A0. And there's some more stuff which falls away. I think that's the better. I mean, of course, it's very imprecise, but I think there's something in that direction.
Okay. If there, maybe this is in any case a good time to thank the speaker again. And then